Okay, welcome back. So, we had previously talked about heat transport through conduction, through direct contact. And now we're going to talk about heat transport through convection, where the heat is moved from one thing to another through the intermedium of a fluid. You have some hot thing over here, some cold thing over there, and from the hot thing, the fluid moves and carries the energy to the cold thing. And so the fluid can be, as stated up here, it can be liquid, can be gas, can be plasma. All of those are examples of fluids. Now we can do this in a couple of ways. We can do this through forced convection, where you have something mechanical that's pushing or pulling the fluid around, like a fan or a pump to push stuff through pipes or whatever. That's one way in which the fluid can move and carry that energy. But it can happen without any mechanical devices as well. It can happen with natural convection through a process and that we can describe with the principle of buoyancy. So I'll write the word down, and I want to show you an example of that that we get in a regular old lava lamp. So buoyancy. Okay, so over here we've got a lava lamp. And the lava lamp is constructed so that we have a light bulb down below, and where it's hot, there's a couple different fluids in here. There's the fluid that's some kind of oil, and then where the blobs are, their own fluid that's more of a waxy fluid, where the blobs are rising up. And those blobs, we can see them going up and down. The other fluid is also moving, but it's less visible. And it's taking the energy from the light bulb at the bottom, delivering it up to the top, and releasing it, and then sinking back down so the process can start again. So the way that this works is from buoyancy, and let me a little bit higher again. Sorry, and straight on. Okay, so buoyancy was described in an early way by Archimedes about 2,200 years ago. Archimedes was a famous engineer and scientist of his day. You may have heard of him before. He developed the Archimedes screw, which was a simple machine that basically used a rotating ramp to transport water up from a deep well. He described the law of the lever, which how if you have the longer the lever that you are using, the less force that you need to apply to get a big output force on the other side. He developed a variety of siege defense tools for the city of Syracuse, which is where he lived, and where his relative ruled, King Hero II. So Buoyancy, he also wrote about and described what became known as Archimedes' Principle, which the development has kind of a legend that goes along with it, which you may have heard of. And it goes like this. So Archimedes' relative King Hero had commissioned an artist to craft a gold crown to go on the head of a statue of, I believe, Zeus in the temple in Syracuse. And the king supplied the gold to the artist, and when it was done, the king suspected that the artist had embezzled some of that gold rather than use all of it for the crown, and had instead substituted some lower priced metal. And he wanted to know whether or not he had been cheated and whether he could do that without damaging the crown. And so he called his relative Archimedes, and Archimedes went to think about it. And the story goes like this, that Archimedes, while he was pondering it, he sat down in his bath. He went to take a bath. He sat down in the bathtub and noticed that as he sat in, not only did the water support him, but some of the water overflowed and went out of the bathtub. And when that happened, he realized that the weight of that water that got pushed out by him was equal to the amount of force being pushed up on him, equal to that buoyant force. And the story goes that he was so excited about this discovery that he leapt up out of the bathtub without bothering to put any clothes on and ran through the streets of Syracuse to the king, naked, shouting, "Eureka!" which it was Greek for "I found it, I discovered it." So that's our story, that's our legend. But the Archimedes Principle itself says that the buoyant force is equal to the weight of the displaced fluid. And what does that mean? It means that if you have, some object, maybe it's an ice cube in water, and here we have ice, here we have water, and this much of the water is being displaced or pushed out of the way by the other object. And an amount of water that would fit in that volume, however much that water would weigh, is how much buoyant force is pushing up on that ice. We could call it the missing water. And if it's floating there, not rising or sinking, then the buoyant force and the ice's weight are the same. And we have buoyant force. You experience buoyant force as well when you go in the bathtub or go in a pool or the ocean or lake or whatever. You don't have to even sink for it. You drop a rock in a bucket of water. The rock is experiencing buoyant force as well, even though it's not enough to make it float. But it is enough that if you were like hanging it from a scale, that there would be less force pushing down from that rock, or pulling down on the scale from the rock, because some of it would be supported by that buoyant force from the pressure of the water all around it. That's how it comes from also. It winds up being the difference in the pressure coming from below compared to the pressure pushing down from above. There's that much more weight of fluid around it between the top and the bottom of the object, or the part that's below the fluid and the bottom, that you get some upward force. And so this is how, if you want to figure out, one way to figure out what fraction of your body has got body fat versus muscle and whatnot, one way to do it is to weigh yourself dry on the land and then see how much you're pulled down when you set yourself in water, and look at the difference there, and that can help figure out that difference is going to be related to how dense you are compared to the water, and that can tell you how much fat and muscle you've got. So that's buoyancy in general, and it relates to convection like this. So we have some high temperature stuff down below. It could be the heating element on a range on a stove top. It could be the mantle, or it could be like the core of the earth. It could be the light bulb in that lamp. It could be a radiator in a room. And then you have lower temperature up above. And what you have going on with this is that you're going to have heat enter from below. And the fluid, when the heat goes in, it's going to do like those blobs did. It's going to do like a hot air balloon does. The temperature rises. The temperature rises, and therefore the volume increases. And so the density decreases and the buoyant force increases. If the buoyant force increases, that means it's going to get bigger than the weight of the surrounding stuff. bigger than the weight of the heated stuff. And so it's going to rise. So it goes up. It inflates like a hot air balloon because it's been heated up, and the buoyant force pushes up on it. It's displacing more fluid, increasing the buoyant force, making it rise. And then it gets up here. It gets up here to the top, and the heat leaves into the low temperature material. And so this means that the temperature is going to go down and the volume will go down. And so the density will go up, and buoyant force will decrease. And it will be less than the weight. And so it sinks. And it gets back down to the bottom again, and the whole process can start over. It can grab more energy again, heat up, expand, push away more outside fluid and make its buoyant force bigger, rise up, cool down, or release that energy, cool down, shrink, have a smaller buoyant force so it sinks, and it just keeps on going and going and going. You heat up soup or water or whatever on the stovetop, and you see this all the time. You get happening what we call a convection settle, where you have fluid rise and then cool down and drop again. And form this circular pattern. We have this happen inside the Earth because over geological timescales, the magma moves under the Earth, but the rocks expand and rise as well over really long times. And if this was the rocks in the Earth moving, then you get a situation like you have at the mid-Atlantic ridge. You can have an ocean spreading center where this makes, a little bit of magma comes out and it pushes the continental plates along and it expands them, and the plates spread apart there. And then they can dive underground again, getting pulled down by the other side of the cell with convection. This happens on the Earth with our weather systems. It can happen on a small scale with high pressure and low pressure centers. It can happen on a large scale. It happens on a large scale with the large bands that the overall weather system of the planet has. we get on the Earth, this happens in roughly three zones per hemisphere. If we're looking at the Earth here, and we'll call this north and this south, you get it rising up and sinking, rising up and sinking there, and sinking here, rising, sinking. 3 zones per level, and they also and in doing that they also circulate east-west differently. So the mid-latitudes, this whole band goes from west to east, and it goes from east to west, near the up in the Arctic as well. And these divisions, that's where you get your stuff like your polar vortex. So this boundary comes down further south, you get colder air coming in. It's a funky, complicated system because the whole thing's spinning on top of that. You get different numbers of these things on different planets. So you see there's all sorts of bands on Jupiter. If you look at Venus, it's like one band. It moves so terribly slowly, you get less of this circulation going on. Also because it's a fairly constant temperature there. So that's all I've got to say about convection for now, and that's plenty. We'll do another lecture about electromagnetic radiation.